don't have much time. Yeah, tell me.
Sir, when will we get the results of assignments? Means will they be declared or we won't get?
No, that will be decided by the coordinator, right? Tutorial teachers take very simple question I have given. It's difficult to now I can they will be evaluating. Just hold on a minute. Okay. Yeah. You have any doubts?
Sir, hello.
Yeah.
Hello, sir. Sir, just before starting, sir, if you have any documents on Chiletin, then if you provide that, would be very much good for us.
Yeah. I will. But your tutor, I asked the tutorial teacher to share the Chillet effect slides. They did not share.
Not for us, I think so.
Okay, I will do that. I will do that. Don't worry. I will
Okay,
do.
okay, sir.
I will
Okay.
post in the team. I will upload in the team and I will send a message.
Thank you,
Okay,
sir.
no problem. No problem. Right. So you ask me whatever the material you need, whatever I have, I will share with you. No problem. So my is that you should study properly. That's all. This is the last slide that I have. Before I go to the Redox, I will briefly mention about the catalytic cycle. Right? Please be attentive. We are only 114 students out of 180 plus or 190. It's very poor attendance. Right. Let's go here, right? You can recall in the last class I have mentioned about the Monsanto acetic acid process is a carbonylation of methanol. Have a closer look at that one. The catalyst, there are two catalysts. One is what I have shown here, that is the rhodium catalyst, and the co-catalyst is the hydrogen iodide, HI. Right? I hope you remember. Right. Now, I wanted to, quickly, right? Maybe another 10 minutes, I will quickly glance through it and I will go to the redox. I will ask somebody, right, what is how many number of electron for this complex? The red color box, rhodium, I2CO2 minus. Can you tell me what is the number, how many number of valence electron? Anybody? Yeah, I will ask. That's a mystery. Prabal, Prabal Kumar, age
Yes.
one. Yeah, tell me, Prabal. How many electron? No problem. Even if you make mistake, then only we learn, right?
Okay, sir.
Yeah.
I'm counting it.
Yeah. Another one of you count the blue box. After the oxidative addition, the blue box is there. One of you count. I will ask whom? Abhishek Das. Abhishek Das, you count the number of electron for the second species, the intermediate. Yes, Prabal.
Total is 45 atomic number. 1 second, sir. Rhodium and 4 electrons from iodine.
Abhishek, second one. Tell me how many number of electron?
Either says,
I think you are not. No. Yeah.
8 और rhodium आता कौन सा ग्रुप में?
Others, anybody?
3, 5, 5.
Sorry?
9.
Sony Aditya.
Sir,
Yes, sir.
Count the number of electron for this the red color box complex. Prabal, did you get?
Sir, 18.
18? No, my goodness, this is a serious problem. Then,
no, sir, that means what are you asking for?
Valence electron for the complex. Valence electron for the complex. Last class I taught, right? I said that your tutorial teacher did not teach you the counting the number of electron. They should have done.
Yes, sir, she taught.
Yeah, right. Anybody? There is a 16 electron complex. I don't have time to show you, right? The rhodium is.
Sorry, I'm mistaken there. Iodine is giving 1 electron. I counted that as 2.
Yeah, halides gives 1 electron, carbonyls give 2 electron. You have a 1 negative charge, right? And then you have your the central metal rhodium valence electron is 9. Okay, it will be totally 16. The second one, anybody? I asked for Abhishek Das.
18 electrons.
18 electron, right? I hope you followed that, because we do the oxidative addition. That's one way to easily find it out. But you need to count the number of electron basically. What we have, you have a 3 iodide, 1 methyl and 2 carbonyl, 1 negative charge, overall negative charge, and the valence electron is 9. So you have a 18 electron. I hope you understand how do I get to, you have to calculate the neutral atom method. You find out the valence electron. Don't go to the oxidation state method. Do the neutral atom method. That will be quite straightforward. And count the number of electron contributed by each and every ligands. Carbonyl contribute 2 electron. Methyl iodide or halide contribute to 1 electron each. Right? Okay. So your oxidative addition, you got the 18 electron complex that is coordinatively saturated. On the other hand, the starting complex is coordinatively unsaturated. I hope you follow. And then where migratory insertion takes place, then again it becomes a 16 electron complex. Why? This acyl, right? You have instead of your carbonyl, you have an acyl group. You can count the number of electron. And then association of a carbonyl ligand, again it becomes a 18 electron complex. And then followed by the reductive elimination, you get this product, and then comes your hydrogen iodide, the co-catalyst come into play, and then you get your methanol. Sorry, methanol is starting, then you get acetic acid. Acetic acid you are getting, right? So in general, let me go back. Now what will happen in a catalytic reaction? Now what's happened? Number one, please note it down. Your oxidative addition, I explained already. I'm not going to again explain. And then your association, dissociation of ligands. So during the oxidative addition, what happened? The oxidation state, right, increased by +2. The third one, what we have is the migratory insertion, right? I have explained in the previous class. And the fourth one is what we have is typically, right, reductive elimination. In between that, other steps also can come into picture. I have explained you the various steps that is involved. Association, dissociation. Major step is, right, oxidative addition, migratory insertion, and reductive elimination. These are the 3 to 4 steps that mainly come into picture in a catalytic reaction, right? This is one of the reaction that is basically a recent literature. Just have a look at that one. Again, this is basically a carbonylation of methanol, but with a different catalyst. Because the Monsanto process, that efficiency and handling is somewhat difficult. People have come up with a different catalyst. That is, again, you have a rhodium catalyst along with a co-catalyst of ruthenium and hydrogen iodide. Okay, multiple cycle comes there. This just to inform you that it is not the old story that we are talking about. This is still recently. This is a 2016 Nature Communication, the top journal that publishes one of this kind of work. It's a catalytic reaction. The yield is pretty good, right? The right hand I have shown, corner I have shown, right? 70.3% yield with a turnover frequency of 30.8 hour inverse. That's a pretty good yield. That's the reason that was published in the journal. That's what we call the Nature Communication. Don't much bother about it. There are continuous work is going on for the synthesis of methanol, acetic acid from methanol. Again, there's a recap. I don't have a time for asking you several questions. Maybe tomorrow, after finishing the class, I will bring some of the videos and some of the problems put it there. We will discuss it. Again, this is the first catalytic reaction that we have studied. That's a hydrogenation of alkene. What was the catalyst that we use? That is a Wilkinson catalyst. That's the red color box. That's a 16 electron complex. Okay. As I said, oxidative addition. What is happening? The hydrogen is going into added. Now a new species is formed. and then ligand association, ligand dissociation in order to accommodate the alkene, right? A pi complex formation. For that, the ligand dissociate, and then alkene coordination takes place, followed by migratory insertion and ligand dissociation and reductive elimination. So I hope we should be straightforward. What you need to understand is that the different steps involved and the number of electrons that are involved in the complex. That's more important, right? How many electrons are involved? Sequence of the step sequence you remember. Oxidative addition followed by ligand dissociation, coordination, migratory insertion, ligand association followed by reductive elimination. So at the end of the day, because it's a catalysis, you should get back your catalyst. You're getting back your Wilkinson catalyst, right? Okay, right. I mean, this is a one representativity example, right? Last class, I did not explain you this migratory insertion with this diagram, with this representation, right? What we have here, you have a L, here you have your complex here, and then you have the L coordinated complex here. Okay. Now, what's supposed to happen is that a migratory insertion takes place. Okay. This is a general, this one. Now, look at here. Here, what I have shown. Here is a typical example. Here I have a hydrogen. Here, this is the alkene complex. What is happening here? You have the migratory insertion takes place. Yeah, you go here, and then as a result, it comes here. So why I have shown here is that the reason is you may be asked to find out the migratory inserted product, not necessarily from the hydrogenation or from your Monsanto acetic acid synthesis. Any type of this one, you should be able to find out very straightforward what should be the product of this reaction, the migratory insertion product, right? That's the reason I have given here. Okay. Yeah, I have given another example for reductive elimination. Right? Reductive elimination is the last step. Oxidative addition is considered to be the first step. If you are referring to some of the textbook may say the ligand dissociation is the first step. Don't get confused. What I teach you for, right? Reductive elimination is the last step. At the last step, what we get? We get the product and the catalyst back. So this is a hydroformylation reaction. Don't bother about the name. Basically, what we need to know, what is the product that is coming out. This is the complex, and the product process is reductive elimination. I get an aldehyde and I get back the complex. Okay, I hope you are following. This is another Cativa process. This I have mentioned. This is a methanol to acetic acid, but using a different catalyst. What is a catalyst? Iridium catalyst, right? That we call as a Cativa process. So here also what we get the product iodide, right? Not the acetic acid. This should undergo hydrolysis. Then we will get the acetic acid. But what I want to bring to your attention is that the reductive elimination examples, how you are getting back your catalyst and the product you are getting, right? Okay, this I have already explained. That I am not going to explain again this one. Already 20 minutes is over. So to brief it, in the catalysis and organometallic chemistry, what you should know is counting the number of electrons. Follow the neutral atom method and do a lot of examples. I mean, your tutorial teacher should have given enough example. Tomorrow, if time permits, I will throw some examples for you to calculate. Okay, so you take many examples and work out. Right, look at the table, how many electrons the ligands contribute in the neutral atom method. Follow the only one method. And then we studied about the catalysis, what are the different steps involved, right? Your oxidative addition, your association or dissociation, migrative insertion, at the end you get your reductive elimination. Okay, so that's all about I will post these slides this evening. You can quickly go through it. If possible, I will add up some of the examples. You can work out the calculating the number of electron and other thing you can do it. Okay, right. Anybody has any doubts? Okay, right. I hope you follow what I taught in the organometallic chemistry. Organometallic chemistry basically deals with the bonding of carbon to metal. We typically started with the carbon monoxide. The MO diagram that you remember. That's the one of the questions in the assignment. Carbon monoxide is a very good pi acceptor. How will you explain? So you need to have your MO diagram, and then you explain that how this carbon monoxide function as a pi acceptor. So now our second topic, the last topic, is that redox reaction or oxidation reduction. Here, what we're going to talk about is you should have learned about the redox table, right? Yes or no? Redox table? Anybody? What did you understand from the redox table? Aniket Kumar Gupta, can you tell me? Aniket? Aniruddha? Am I audible?
Yes, sir. Yes, sir.
Yeah. Aniruddha, please tell. Aniruddha Panda, what did you study in the redox table? In the JEE syllabus, you should have learned so much about redox table. Can you tell me? Anybody? Bajaj, Aniruddha, tell me.
Actually, I forgot.
You forgot. Okay. Anybody else?
Sir, reduction and oxidation strength table.
Yeah, same table. Looking at the potential.
Sir, the one that gets most easily oxidized is sodium, that is at the top, and sodium.
Very good, very good. Right. When you look at the redox table, you will be able to see that from the potential, you will say that which will be reducing, highly reducing, which will be strongly oxidizing. Right. You will be able to tell that looking at the potential. That's what we learn. Right. That's a redox table. Right. But it's not only that, redox chemistry, that's much more than that. Much more than that. So in this topic, what we'll be learning that it's not only limited to A plus the reduction potential. From that, you find out whether it's a reducing or oxidizing. It much more than that is the chemistry, how we can study that is involved. Say, for example, A, this is a redox couple. Say, for example, you know the potential minus 0.5. Let's say, for example, minus 0.5. Now, looking at this potential compared with the other species, you will be able to deduce whether it is reducing or oxidizing. You will be able to say. That's all the redox table said. But it's much more than that. The chemistry is completely missing. What I mean, the chemistry, maybe there are other species involved within this redox couple. So how do we know that? For that only we are going to study here. Okay, this is an interesting topic, right? I don't know how you enjoy the redox table and redox chemistry. In the JEEs, the students should focus much on this topic so that they can be able to easily score more, right? So the redox reaction is in biology, right? I will show you example. And industry also it is there. And of course, in the environment also there. We can see all this in the biological, the redox reaction that is taking place, and in industry as well as the environment. Biology, what I'm talking about, I'm not sure how many of you are familiar with this cycle. This is an electron transfer cycle. Electron transfer cycle in a typical living system, right? Transfer cycle, right? Is a multiple redox reaction takes place. Say, for example, NAD is getting converted, nicotinamide adenine dinucleotide, it is converted to the NAD plus, and then iron sulfur protein, flavin, coenzyme Q, and then your iron sulfur protein again comes there, iron copper protein, all these are coming there. You know what is happening? Oxygen is released, right? At the end of one cycle, oxygen is released, but involving so many number of cycles of electron transfer. All are basically a redox reaction. Redox reaction, those who go for a biotechnology or those who study chemistry further, second year, you will understand this, what actually means here. It's a quick look at the table here. The biological redox reaction, the potential I have mentioned here, cytochrome C, your ferredoxine, and many other redox reaction that is involved in the biological process. Now, second one, this is just to highlight that redox reaction is just not just to calculate the potential and find out whether it's thermodynamically possible or not. It's not that. It's much more than that, a practical application. So the industry, what we have, the extraction of elements. So in your class 10, 11, 12, that including your JEE preparation, you should have studied the extraction of elements, a different process involved, right? I'm not sure how many of you have heard about the thermal reduction. Carbothermal reduction. That is, you take your ore, that is basically an oxide, and add up carbon. That's what the furnace that is shown here, right? You treat it, heat it at a particular temperature. Your ore is basically converting and getting your metal, pure metal or impure metal you will be getting. That's basically a redox reaction. Not only that, the supercapacitor and battery. All of you have your mobile devices or the gadget that you have, all are powered by a supercapacitor or battery. There, what is happening basically is the redox reactions. Either the intercalation or electron transfer reaction that is taking place in the supercapacitor or your battery that you have in your mobile devices or your laptop. And the last one, environment, that you should have seen. This is another redox reaction. There's a very beautiful example where you have what we have, the rusting of iron. A typical electrochemical cell that is formed, nobody dictated, it's a spontaneous process. Oxygen reduction taking place, and the iron is getting oxidized. As a result, what you are getting, a product, what you call the rust. That is typically a redox reaction in an environment that is open space. You have an electrochemical cell, and there you have your redox reaction that is taking place. I'm not going to explain all this. This is for dummies that you are very familiar with. This is how you do the oxidation and reduction. This is not. Before I go to here, carefully listen carefully. Look at the slide. Right, it's a little lighter, like on the lighter side of redox chemistry. On the lighter side of redox chemistry. It's an interesting story. I'm not sure how many of you have heard about this person, right? He was the one who discovered the artificial sweetener, called the saccharin in 1879, right? What we call the Ramsen, right? 1846 to 1927. Very quickly, we don't have a time. Usually I show videos, but because of the lack of time, I will briefly narrate the story and then go. He was like you, was a young chemist, young graduate student in a college, right, in the university. So he read that the nitric acid acts on copper, right, when in the 18, right. He was so curious to find out, right, what actually that nitric acid acts on copper. So he was curious. One day he went to the lab early, well before others entered the lab. He saw the nitric acid, concentrated nitric acid bottle that was lying on the table, and he pulled out the copper penny, copper coin, and put on the table and opened the bottle, nitric acid bottle. Just he wanted to know how the nitric acid acts on copper. Right? He was so curious to find out. So he poured the nitric acid over the copper coin. So I hope you understand what he might have observed, your violent reaction, right? He was so scared. Right, he was so scared, he immediately picked up the coin and ran to the window and threw it to through the window. And he looked at the finger. The finger is completely damaged, in the sense full of yellow color. Now he understood that nitric acid not only acts on copper, it acts on finger. Right, now he felt the pain. He was started rubbing over his trouser. Right, because little pain and the yellow color, dirty looking finger. So he started rubbing it over his trouser, and then looked at the trouser has gone, right? So nitric acid not only acts on copper, it acts on finger, not only on finger, but it also acts on the trouser. I hope you understand the power of redox chemistry, right? There's a redox reaction that took place between your nitric acid and the copper, and then followed by your finger and so on, right? This is on the lighter side, right? So I have a video, but we don't have a time. We'll go back here. as I mentioned earlier, that's what will a strong reducing agent and weaker reducing agent, a strong oxidizing agent and weaker oxidizing agent. This is what we learn from the redox team. Is it all about, do we have something more than that? What about the chemistry of a particular species? Say, for example, I will be taking the chlorine. I will give you that with a different perspective. How we'll be able to interpret. Now, what I see here, Cl2. Yeah, let me make us put a square mark. Right. What I have here is that Cl2 to Cl. Let me zoom it. You will be able to see. I have a potential of 1.36. From this, you will be able to tell that whether it's oxidizing or reducing, depending on it. It's a relative term. Right? Is it all about? No, it's not all about that. We have much more than that. So in this one, what we're going to learn is that we are going to say that the diagrammatic representation of the redox data. That's what we are going to say. Right? The diagrammatic representation of redox data or potential data. There are different data ways there. Well, number one, what we have the Latimer diagram. This will be studied. That is basically developed by Wendell Latimer. And then another one diagram, Frost diagram, that was developed by Arthur A. Frost. So these two diagrams, there are many more diagrams are there. One of the diagram you should have already studied, Allen-Gum diagram, right? I hope you can recall. Your class 12, the syllabus has that Allen-Gum diagram. Another one diagram, we have a Bohr-Bax diagram that will not be going there. So we'll be stick to these two diagrams, the Latimer diagram and the Frost diagram. So let me explain you what actually the Latimer diagram. One by one we'll learn. Today I will explain you the Latimer diagram, and then followed by the next class. What we'll do is that let me write. At least you follow it. What we're going to talk about the Latimer diagram. LD. Let me put by this one. Latimer diagram. So this basically you are representing. You are representing. Somebody is raising. You are basically representing the redox data or the potential data in a different form in order to understand the entire chemistry of the particular species involved. Say, for example, we talk about the Cl2, Cl minus, right? We know that 1.36 is the potential. That's all we know. Do we have any other species? What is the chemistry? We have no idea. Now what we do is that we'll represent. I will make it general. Say, for example, this is M5 plus. This is one of the species, right? Whether it be a metal or non-metal, or a halide or whatever it may be. What we do is that follow me, right? M4 plus, now M3 plus, and so on. It goes M. You have your 2 plus, M plus, and then you go here M0. Okay. So in a sequence, we are writing the different oxidation state, possible oxidation state. Over that, you write your potential, X volt, Y volt, and so on, and so on. So there won't be any arrow. Some of the textbook will show arrow, but typically, original list, there is no arrow. This is basically what happened is that you have a M5 plus to 4 plus. What is the reduction potential? This is the reduction potential. And then 4 plus to 3 plus is the reduction potential. And here your 3 plus to 2 plus, and so on it goes here. All the reduction potential are listed, enlisted or represented in a particular, in a single diagram. So now I not only know only this potential, I know all the possible oxidation state exist for Mn plus or M0. All the possible oxidation state, I will be able to find it out from this. Now, looking at the reduction potential, I will be able to predict, I will be able to tell that what are the species will be stable or which will undergo disproportionation reaction or which will be a highly reducing agent or which will be a highly stable species. All this I will be able to look tell from the single diagram of Latimer. Right, that's what we say Latimer diagram. Right, I hope you are getting this. Nothing but all the possible oxidation states of a particular element is represented in a single diagram with the reduction potential for all the species involved in the conversion of the species. I hope you got it. Right. Let me go here. Right. What we have here. Yeah. Typically now. Right. What we have, as I said. Right. M5 plus, M3 plus, M4 plus may not be there. Like not necessary that. Right. Maybe not stable. Right. M plus what? These are, I mean, general description. M0, maybe some of the elements may have a negative oxidation state. That also should be represented here. Quite straightforward. What you need to remember that this is basically arranging the higher oxidation to the lower oxidation possible and providing all the reduction potential. From this, we will be able to understand the entire chemistry of what the chemistry I'm talking about. M plus 5 to M minus 2. All possible chemistry I will be able to describe from a single representation. I don't need to go and look at for each and every species in a redox table. All the redox table may not give you the reduction potential of all the species. Now in a single diagram, what I can do, I can understand the chemistry of all the species involved in the redox couple, say for example, M plus 5 to M minus 2. Okay, that's quite straightforward. I will be taking chlorine as an example. I will illustrate you. How do I study the chemistry of chlorine? It looks like it is only 1.36. Okay, you will see that it's highly oxidizing. No, beyond that, what and all is involved there? Look at here. Usually, if you have a time, I will write down each and every step in the blackboard when you are when we have the class offline. Because of the limited time, and then we are doing it online, I have already put it here. Now, see here. What I have shown here is, carefully look at, forget about the red and blue box. First look at here. ClO4 minus, that is a perchlorate. I hope you are following, perchlorate. And then you have a ClO3 minus chlorate. And then you have a HClO2. And then HClO, Cl2, Cl minus. Same, the chlorine species involved, but you have a 5 different oxidation states, right? I hope you are following. In a single diagram, a single representation, I can understand all the possible oxidation state, and I can get to know all the reduction potential of the species. Okay. Say for example, ClO4 minus to the ClO3 minus. This is basically what I've been doing in acidic solution. Same thing is possible in alkaline solution also, right? Now what we have, ClO4 minus to ClO3. Now what is the potential involved? 1.2. Yes, you will say that, sir, what is new here? Yeah, it looks like nothing is new, but in the redox table you will see only your Cl2 to Cl minus, that is equal to 1.36. That's all you know. Remaining species of chlorine, we are not aware of that, or if you want to understand, you need to look for another table. So, but here you have all the species involved, right? Now, what we can do is that we can do little more than that. I'm not going to do the balancing. I hope you all know that. Now, this is the redox couple that I have red mark here. What I have done is that I have balanced the equation, right? Balance the equation from the original couple. I'm writing and the balancing this one. The same way, what I have is HClO to Cl2. There also what I have a redox couple with a potential of 1.63, which is much higher than the Cl2 to Cl minus, that is 1.36. Now you will be able to compare the reduction potential and predict the property of the species involved. Right? Again, balance the equation as straightforward. Right? Some of your tutorial teachers will give you example, work out many the problems regarding this one. Now, going to this one, what we have here is how to extract the potential of a non-adjacent species. Look at carefully, right? Please don't overlook. It's quite straightforward. Yes, sir, I can do it very simple. I will have a look at and I will do that. Most of the students have an overlook, and then at the end of the day, they will make a mistake, right? Now look at here. How do I do that? Now look at this couple. That is, let me blue mark it. I blue mark it here. This is the blue box. Blue box you look at here. What I'm doing is that HClO to Cl2 is 1.63. And then Cl2 to Cl minus is 1.36. Now what I need is that I need the potential of HClO to Cl minus. You may be familiar with this one, right? I don't say no, right? You might have come across, you would have calculated in a different way, but with the help of the Latimer diagram, how do you get it, right? Basically, what I need to know, right? You can read it there. Identify the redox couple. It's given here. Now you have your redox couple 1 and redox couple 2. Basically, what we have is that you have your 1.63 and then 1.36. That is corresponds to the second redox couple. And this is the formula that we use. Right? I mean, I don't even call this a formula. It's simple relationship, right? Basically, from the delta G, we cannot simply take the potential. We'll take the delta G, and then from this, what we have, we calculate the potential of the non-adjacent redox species. The oxidation, the E0 of non-adjacent oxidation state. That the E0, the question mark that I put, I have shown here. That is basically a 1.5 volt, right? I think nothing much to explain here. It's rather straightforward. What you need to know that you need to know this, how the relationship E equal to NE plus N double prime E double prime divided by N single prime plus N double prime. That's a straightforward. You can calculate the reduction potential of the non-adjacent species. I have given again another example. Have a look at. Have a look at. If you have any doubt, you can ask that. I mean, there should not be any doubt. It's a rather straightforward, simple mathematics. Basic solution. What I have given here, the chlorine in the basic solution. So what you need to remember is, it's not limited to this chlorine. Say, for example, listen carefully. Suppose I given the Latimer diagram of 2 different elements, and I ask you to find out the possible reaction between the redox couple of the 2 Latimer diagram that I am giving. Whether this will be thermodynamically favorable or not favorable. If it is favorable, what is the delta G? What is the E0 value? That will be you will be asked to calculate. Not simply your single Latimer diagram. Maybe, say for example, I have a M N plus goes. That is M minus 2. This is what one Latimer diagram. Okay. Another Latimer diagram, what you have is the chlorine. So you are given the chlorine Latimer diagram as well as the blue oval shaped Latimer diagram. So you are asked to find out the possible reaction between one of the couple in the chlorine and one of the couple in the Mn plus Latimer diagram, and find out whether the reaction is feasible or not. That is the key that we need to learn here, right? Okay. So again, this is straightforward, non-adjacent oxidation state. How do I find it out? Using the same. That's another only example. That's basically ClO minus to Cl2. Now, one thing you should note it down, in acidic as well as in the alkaline, the potential is largely different, right? I hope you understand, right? This is in your acidic solution, first one. This is the second red one is in the alkaline solution. If you look at here, Cl2 to Cl minus is remain 1.36. That tells us a powerful oxidizing agent, either in the alkaline solution or in acidic solution. But you go back and see here, now say for ClO4 minus to ClO3 minus, the potential is basically largely different. Here it is 1.2, here is a plus 0.37. That will tell you the oxidizing or reducing power of the species in a particular pH, whether in acidic pH or in your alkaline pH. So if you are given 2 diagrams, that is one in acidic, another one is alkaline, you will be able to predict the property simply looking at the potential that is in the right. Okay. Another one thing, important thing that we learned from the Latimer diagram is the disproportionation reaction. I hope you know that what is disproportionation reaction. Spontaneous oxidation and reduction reaction. Right. What I have here is M plus. I have a M plus here. The blue color circle I have a Vm plus. This undergo spontaneously oxidation and reduction reaction. Oxidation and reduction reaction. If that you get your M2 plus and then get your M0, right? Both you are getting. Okay. So simultaneously it goes there. So this species is what we call the undergo disproportionation reaction. Now, how do I know that? In the chlorine Latimer diagram that is given, how do I know that? You can look at here, look at the potential very carefully, right? I have written very carefully, right? The potential on the left of the species is less positive than that on the right of the species, but that can oxidize and reduce itself. The process what we call is a disproportionation reaction. A simple thumb rule, we can work it out whether it is a thermodynamically feasible reaction. Yes, both reactions, the oxidation reduction reactions, both the thermodynamically favorable reaction. What do you need to remember? Look at here. Cl2 to Cl minus is basically 1.36. That is higher than what we have the left hand side potential, that is ClO minus to Cl2. If this is the case, what is the case? Whenever the reduction potential of the left hand side is less with respect to the reduction potential of the right hand side couple, then what we implies that the middle species, who is that species here, Cl2, this species will undergo disproportionation reaction. Right, very simple. Just look at and then find out that yes, this is undergo disproportionate reaction. Now, one thing is that whether it's spontaneous or not, we should prove that. Right, next slide you see here. It is thermodynamically feasible. Now, this is the couple, the blue colored rectangular. That's the species that we're talking about. I am telling that this the Cl2 in the middle undergo disproportionation reaction. Okay. Now you see here Cl2 to Cl minus. This is the potential. ClO minus to Cl. This is the potential. Now you write here. Now go here. The potential E0 is basically positive. As a result, the reaction is spontaneous. In your case, because it's online, it's very easy. You need to bubble only, right? Subjective type means we can twist the question as much as, but now we are limited, right? But please don't overlook how we find out the disproportionation reaction. What we need to remember, look at the potential on the left hand side and the right hand side, and then predict whether this will undergo disproportionation reaction or not. Right. Now, I have given up another Latimer diagram. Right, Latimer diagram is at the bottom. Right, I have, you can go through it. Latimer diagram is here. Right. Next slide, I will complicate this Latimer diagram little further, not to confuse you, to make you understand the chemistry. Right. So, what happens? What happens when iron reacts with H plus? You drop the iron fillings or iron rod into the acid. What happened? Right. There are two possibilities. Fe2 plus, Fe3 plus. There are two stable oxidation state. We know that, right? Now you have your potential. How do you find out your Fe3 plus to Fe0? Yeah, you can read that. This is for dummies, right? I don't need to explain. I hope you may not expect me to explain this one. We don't simply add E0 because E0 is not a path independent, not an independent state function. Is a path, G0 is a path independent state function. So we must first convert E0 into G0 and then we'll do that. That's what I have shown here. My point is not that one. That's very straightforward, right? My point is something different here. Now you see here, the iron here, the red color circle, and then a blue color circle is your Fe3 plus, and my black color circle is the Fe2 plus. Look at the potential, right? The number one, so this is a 0.036 and 0.04. I'm bringing here to this diagram. What is the diagram? Look at the bottom that I have delta G0 and then oxidation state, right? Now, looking at the delta G0 value with respect to oxidation, which is the most stable species? Yeah, obviously Fe2 plus. It doesn't mean that Fe3 plus is not stable. No, right? Don't come to the conclusion. With respect to Fe3 plus, Fe2 plus is more stable, right? So we read much more from the potential diagram, and then now by bringing the red color box, so entire diagram is given, right? Fe3 plus 0.77 to Fe2 plus minus 0.44 Fe, and the non-adjacent species that is minus 0.036. So this is the simplest diagram for iron. Okay, right? Not much is there. Suppose this is how do I get? I have a beaker where I have an acid and I put a iron rod. Now I follow the potential. I made this one. Now what I do is that I add a little bit of Cn minus, the strong field ligand, right? I hope you remember the weak field and strong field ligand that we have studied. I add this to one. What will happen to the equilibrium? What will happen to the potential? Cn minus will definitely undergo complexation with either the Fe2 plus or with the Fe3 plus. Obviously, it will take place. Now we look at here. This is what, right? Whatever I have shown here, this is what I have. I am repeating, right? Not new. The red color rectangular take this one, and the black color rectangular table, right? The box, both are same. Now, as I said, what I'm adding, I am bringing Cn minus. That's a ligand. Here it is a strong field ligand. Now, what's happening? You have your FeCN6 2 minus, FeCN6 2 minus. The oxidation state remains +2. On the other hand, here you have your Fe3 plus oxidation state, but it is a different complex. Now look at the reduction potential, that is completely different. Why it happens? Though the +3 oxidation state, and here you have a +2 oxidation state, but what is happening here is that the potential completely changed. Why it changes? Because of the complexation. Cn minus complexation that modulate the reduction potential. So what are the common? The concentration, temperature, other reagent which are not inert all come into picture, right? So it's not only for a simple element, but also the complexation what is taken. This is basically Cn minus. It can modulate the redox center, that is iron, right? Reduction oxidation property it can modulate. Either it is electron donating or electron accepting. So based on that, it can modulate the reduction potential. Coming to this one, the Latimer diagram oxide is well known, right? Well known example of the disproportionation reaction. Hydrogen peroxide, if you say, for example, by hydrogen peroxide, if you put in the open table, I mean the room temperature, the next day if you come and see that the hydrogen peroxide will not be there, you will have only water. You know why? Can anybody tell that? I said, you buy a fresh bottle of hydrogen peroxide, keep it on your table for a day. Next day when you come there, you will not have the hydrogen peroxide, you will have only water. What is the reason? Anybody?
So that will disproportionate to water and oxygen.
Yeah, as simple as. So how do I preserve this one? How will I stop this disproportionation reaction? Anybody? No, if you have a time, we can interact more on, right? Anybody? Yeah. Pardon? Ronit, tell me.
So by applying a reverse potential or something.
No, I did not get. Little louder.
So by applying a reverse potential.
By applying a reverse potential, what is that? What potential I will apply? I have a see. I am a layman. I have only the bottle of.
You have to store it in some inert medium. For
Inert
example,
medium. Ron, it's little more clear. Not necessarily inert. Little more.
Kerosene or something as far as
So black colored bottle, if we store it in.
Store it in.
Kerosene or something as far as I remember.
Dark colored.
Because otherwise,
So we have to store it in.
Sir,
So black colored bottle.
Okay, that somebody said that, yeah, store it in the colored bottle. Okay, that also doesn't help much. That I mean, to some extent, it will help for hydrogen peroxide.
So we also sodium fitted like chemicals to
At low temperature.
Yeah, very good. Who is that? Low temperature. Yeah, the hydrogen peroxide should be stored in refrigerator. You know
Yes.
why? That's a simple
Sir,
reason.
because sir, the del G is always less than 0 for in normal day conditions at
Yeah,
room
exactly.
temperature.
Right. I hope you got it. That's
Yes.
the reason. That's
So
as simple as.
reducing
As
the
simple as.
temperature would make it G greater than 0.
Yeah, right. No, so that's the reason the hydrogen peroxide should be stored in a refrigerator. If you are keeping it outside, the hydrogen peroxide will not come and tell you, hey, I am undergoing disproportionate reaction. Is a spontaneous reaction that goes here, right? I have given here the potential oxygen to hydrogen peroxide and then water. Your zero oxidation state minus 2. The potential is 0.7, 1.76. Now, I need to prove that this reaction is the spontaneous reaction because I say you keep it in the open atmosphere in the table. You don't need to open the bottle, right? Even if you keep it outside at the room temperature, the oxygen pressure will develop inside the bottle because of the disproportionate reaction. At the end of the day, you will have only water, right? If you do this calculation, simple calculation, right, 1.23 you will get. That tells that this is a thermodynamically favorable or not favorable?
Favorable.
Favorable. Right. Again, I have explained this one, right? The disproportionate reaction, the same thing. How did I find out? I don't need to do calculation, right? I don't need to go and calculate the delta G because I can simply note it down. This potential is less than the right-hand side potential. Simply look at and then tell that yes, this species will undergo disproportionate reaction without any doubt at all. I hope you are getting right. Okay, right. We again do that. Now I'm coming to a little complex Latimer diagram. Right. What you have seen is an iron and the oxygen is a very few species involved. Now I given a complex diagram. Okay. Right. One is an acidic solution, another one is basic solution. Right. I mean, don't get scared. Oh, this many species, how will you handle that? Rather straightforward, right? Now I have given, I will note it down here. First look at the acidic solution, right? Look at each and every potential, right? Start from here, start from your NH4, N2H5 plus, NH3OH plus, N2, N2O, NO, and then you yourself pick up the species which can, in principle, experimentally whether it goes or not, it doesn't matter. We have the redox diagram. From this, we need to find out, in principle, what are the species will undergo disproportionation reaction. Pick up, couple of you, quick up.
Sir, N2O4.
N2O4.
NO.
NO, obviously. Pardon?
N2O, sir.
NH3OH plus.
NH3OH plus. Right. Now, I hope you understand. How do I get it? This is not something that we mug it up and some magic is given at that. Thermodynamically, we are proving. Right? Okay. Right. I have given here. Again, I'm not going to explain. That is another one. Oh, already 1 o'clock. Right. Just I will finish with this slide. The copper one slide. I will finish it up. You have a class or after a break?
So lunch break.
Okay. Please bear with me. Just a couple of minutes. Only this slide. What I have shown here is the copper, very similar to what I have shown for iron. Right. This is the diagram for potential data. That's a Latimer diagram for copper. What are the species involved? Copper 0, copper 1, copper 2, and copper 3 plus. You may be surprised that does it really copper 3 plus exist? Yeah, in some of the complex molecules, organometallic and all there, it is there. There are some other species, copper minus also will be there, right? Let's not do, I'm not going to take you to the advanced topic, right? Now you will be able to, you can read it from this diagram. What is the diagram that conveys? Copper is the stable, copper 1 is this one, and copper 2 plus is here. I will explain you this little, maybe the next class in a different way when I talk about the frost diagram. right? Now I have shown the difference in the how much the delta G difference is there. It has a lot of implication when we learn about the Frost diagram when we learn that. Yeah. Okay. Yeah. Now I have narrated the story. I will finish this. Yeah. I have narrated the story, nothing but here. Narrated the story of Ira Ramsan. Right. Let me ask the final question and wrap up. He poured the nitric acid over the copper coin. What he observed? What was the violent reaction? Can anybody unmute and tell? It's a concentrated nitric acid. Assume that.
So copper nitrate and nitrogen oxide.
Yeah, copper nitrate. Yeah, CuNO3. Right. What you have a copper NO3 it comes there. Copper nitrate comes, and then
NO2.
Cyano2.
The violent reaction. What is a violent reaction? That's a very toxic gas, a dark brown gas. Tomorrow, if time permits, I will show the video, so you'll be able to understand what actually is there. The reaction depends on the concentration of nitric acid. Yes, Prabal.
So copper oxide, nitrogen dioxide, and oxygen get released.
You will get, basically the nitric acid is very peculiar with respect to the other acids. Right, you talk about the sulfuric acid, hydrochloric acid, or other acid. Nitric acid is too peculiar simply because of the reduction potential that involved in the nitrogen. So it basically oxidizes a copper 0 to copper 2 plus, and you will get a copper nitrate. And in the middle, what will happen? A nitric oxide gas, the violent, toxic, notorious reaction will takes place. Okay, that's a very beautifully interesting chemistry. If I show the video, you'll be able to understand much more on that. Let me stop here, and then if you have any doubt, yeah, I will explain you either in the organometallic side or in the redox side. In any of you have anybody has a doubt, feel free to ask. Anybody?
So actually, I didn't get how to find out whether the from Latimer diagram whether it is disproportionation or not. So can you explain once again?
Yeah, right. What I have shown is that let me take a we'll take this example. Right, here is that. Let me blue mark it. Blue mark this couple. Right. What is it? Okay, that's not taking up. Let me delete it. Okay. Now let's go. Let's take this example. Okay. Now look at here. Rather straightforward. What are the species involved? Copper +1 and copper +2. These are the three species involved. What actually we talk about this the disproportionation? It undergoes spontaneous oxidation and reduction. So here, if at all a thermodynamically favorable reaction, then copper 1 is the fellow should undergo oxidation and reduction. Oxidation to copper 2 plus, reduction to copper 0. So how do I know that whether this fellow will undergo disproportionate reaction? Look at the potential. Look at the potential. Now what I have here is the 0.52, that is corresponding to the reduction of copper 1 to +1 to copper 0. And here what I have, let me mark it in the left hand side, what I have is that a reduction potential corresponding to copper 2 plus to copper 1. Instead of going and doing a calculation whether it's thermodynamically favorable or not favorable, simply the solution is that whenever the left hand side potential, that's a reduction potential, don't convert anything. The reduction potential, what is given? If the left hand side potential is less than the right hand side potential, here what is that? Copper 2 to copper 1 couple is the left hand side, copper 1 to copper 0 is the right hand side. If this is the case, then the middle species, who is this fellow? This fellow undergo disproportionation reaction. To verify, yeah, take the potential, do that calculation, you will get a E equal to positive. That confirm that it's a thermodynamically favorable reaction. This is, I am talking in terms of theory, in principle. Some of the reaction may or may not go in experiment. For your syllabus, looking at the diagram, if the reduction potential on the left hand side is less with respect to your right hand side, the middle species will undergo spontaneous reaction. Got it?
Yes, sir, got it. So actually, I thought that we have to consider only the single reaction. Yes, I thought that CO plus will not convert it into CO2 plus, but we have to consider whole reaction. Okay, so got it.
Yeah. Right. Anybody else? Tomorrow we'll finish the. I hope I will be able to finish it, and then we have a battery. Small topics on battery, and then I will take time. If time permits, I will show some of the video and some example I will give you. Your tutorial teacher will. I have asked the tutorial teacher to solve many problems. They will give you enough examples to solve you in the tutorial class. So please don't bunk the tutorial classes. Right. Anything else? Otherwise, we'll finish.